Thank you, Takashi. I'm Tatsuo Unemi from Soka University in Tokyo, and this work is under the collaboration with the Swiss artist Daniel Bissig. He's not here, but somewhere else in this venue. Okay. So this research, and it's a not kind of research, but the application of AI technology. So it's almost nothing to contribute to any scientific new invention or new findings. So please relax to hear my talk. So this is a kind of sample of artistic application. So yeah, if you might find this your simulation or some of the experiments looks nice, and then you can propose some artists to collaborate with. So yeah, start. So this application of the ant algorithm. So ant behavior is modeled by the distributed pheromones. So both attractants and repellents. So then many researcher were already done by in various fields, ecology and complex system and robotics also. And then, yeah, one of the very nice survey can be found in the Air Life journal by Greenfield and Macado. And then we also did a kind of contemporary application. So that was very nice. That was very nice experience for us. So world famous choreographer Killian employed us to show something like that. So then it was 2008. So at that time, the equipment is not so high resolution, and the computer is a little bit slow. So yeah, something like this. So here is a dancer on the stage. He's moving a little bit faster or slower, and then yeah, you can see some warm is warm roaming with his body. So then mechanism is some little bit easy. So here's the camera, but one of the problem of this installation is that you can imagine there is some lightings and some ornaments on the stage, and then projector itself is projecting some image. So that might be an obstacle to recognize the dancer's position. So then we are using an infrared light in the infrared filter for the camera. So then the computer analyze the image to extract the position and the pose of the dancer on the stage, and then the recognized part is used to organize the a kind of pheromone distribution to control the swarm. So in 2008, camera resolution was the VGA, so very low, and then frame rate is also 30 frames per second. And the projector is a little bit higher resolution, but still low. And then computer was slow, something like this, but big. But last year, it was happier for us. But the problem is you can imagine the camera is usually through high definition resolution, and then speed is also double. So then the projector is also something like this. But fortunately, we could use the very nice, powerful computer of Apple Silicon M2. So then this is the illustration of the plan inside of the theater. So in December of last year, Paris Opera has some program with Iridium pieces, and then one of 4 pieces is our own piece we were involved in. So then this is a very classic traditional style of venue. So it has a 4 layers balcony backside, and then we need to equip the projector and the camera at the back end of this balcony. So the distance is a little bit relatively far. So it's a 30 meter, and then stage width is a 15-meter width. So then in year 2008, it was performed in a Lucent Dance Theater in The Hague. So it's a modern style. So it has the ceiling bridge. So it's a little bit different condition. So we need to adapt to such a scale and distance and something like that. Yeah, and one of the problem is we need to adjust to the many parameters you can imagine. So of course, some of parameters calculation of the projection area or control the visual chemicals, partial chemicals, and the swarm drawing parameters, the behavior also. Yeah, so at the bottom, here is the speed monitors here. So then, of course, we cannot manage the distribution of pheromone in an ideal way. Of course, we need to some methods to simulate on the digital computer. So yeah, as usual, we using employ such kind of distribution model and estimation, and something like this. Yeah, weighted summation of value surrounding such an area. So then we employed two different types of partial chemicals. One is attractant, another one is repellent. And then, of course, we need to simulate the phenomena of diffusion and evaporation. So it's a very easy equation, I think. So just using the Blur effect for this diffusion, and then evaporation just simply multiplies the coefficient little bit less than 1. Okay, so yeah, left finger shows the attractant distribution. So it's a capture indicates the capture area of the target of the dancer's body. And then repellent is used to make individuals more scattered. So each individual secrets repellent each other, and then it's avoid some concentration. So then real swarm is distributed something like this. So then this is the control of the movement of swarm. So each individual has a position and a direction, orientation. And then if it's located at the target area, then it's visible and then it moves slower. But if it's located at out of the target area, then it will take a role of scouting. Scouting means that try to find the target area, catch it, the area as fast as possible. So then it's a speed high. So then each individual sense the density of attractant and repellent from, yes, in this sample, this guy sniffing, sniff 5 points, and then this is the equation to make a force deciding the orientation. So always it's a kind of a greedy policy to find the maximum value of attractant and then less value of repellent. Then this is a drawing method. Yeah, of course it yeah, from the request from the director, Eric, he wants us to draw such individual as a worm. So then we decide to draw the consecutive line segments from top to tail. But of course, we need to keep the length constant. So then something like this. So we need to calculate how many points we should record for each agent. So one of the problems of such an application is that, as you already saw my slides, it has a lot of parameter that should be tuned. So then I investigate the sensitivity and tendency. So one of the difficult points is to tune how much volatile chemicals should diffuse and evaporate. And then another one is how the balance between attractant reaction by individual against the attractant and repellent. So then this is the typical distribution with a different balance of the attractant and repellent. So if the repellent has no effect, then of course you can imagine all of the individual worm is concentrated on the center of the target area. But if the attractant has no effect, then almost distributed evenly in the area. So then we need to tune some this parameter, something around here. So then this is the graph showing the sensitivity for the So of course there are many parameters, so it's difficult to show all of the some high dimensional investigation result. But this is one of the typical thing, just three, I don't know, two parameters. Balance of the avoidance factor alpha, and then each of these such lines shows the different number of window size. So for blur effect. So then we, of course, the left graph shows the how many individuals are involved in target area. So of course, if the concentration is very high, and then it's almost 100% agents are inside of the target area, but too much condensed. So then we need to regulate this value around here. And of course, it's much better to distribute evenly inside of the target area. So then, this the value should be something around here. So of course, this application is strongly rely on the power of the computation. So then we were very happy to use such a powerful computer of multi-core and GPU. So then, of course, you can imagine the swarm simulation itself is a little bit complicated. So then we are using a multi-core CPU. So that Mac Mini has 10 cores, so it's enough. And then it can manage more than some thousands agents. And then, of course, rendering and image processing, simulation of distribution of attractants and repellents is calculated on the GPU. So it's very powerful. Good. And then, it's a summary. We can manage the higher resolution, high speed, and then low latency at this time. And then I want to show you a short demonstration. So unfortunately, we have no, sorry. infrared camera here. So then it's just how to manage it. So they change the color target by face. Here is my face extracted by the image processing, and then this is a swarm simulator. Here you can see swarm chasing my face somehow. Yeah, something like this. And we can change the, yeah, so. Yeah, this is a distribution of attractant. So then this is a distribution of the repellent. So you can see that many of the agents are running around, not in the target area. If there's some dancers moving faster, and then it can capture the area quickly. Okay, so maybe that's it.